Okay, hello everyone. Let's start again with this lecture. As I was saying, today will be a bit more freeform, and I want to introduce the standard algebra and give you an important application which is related to what we discussed last time, actually. So I want to discuss the standard algebra and the homotopy type of MO. So today I'll explain how Tom used the Pontryagin-Tom theorem to actually completely describe the homotopy type of MO, which has two big advantages. Advantage one is that we know its homotopy groups, so we know the actual Bordism groups of manifolds. But even more so, as I discussed with the steroid problem, we can use information about the homotopy type to say something about geometric questions. In particular, today we will see why the map, for example, MO to HF2 splits, which proved that the unoriented steroid problem always had a positive solution. So that's the plan for today. And if we run out of time, and if you don't run out of time, I'll maybe say a couple of things of how you start setting up the Adam spectral sequence, but I'm not sure if we will have time. Otherwise, it will be on Monday. Okay, so let me define. I'll give basically the first definition for a general prime, but the rest of today's class will be for p equals 2. As following a long-standing tradition in homotopy theory of not bothering with signs. So let be a prime. Also because the case of MO, as we will see, the 2 is actually the one that's more important. And since the formulas are easier, I will be. So let me prime the steroid algebra. Is the graded abelian group A upper star, which is the HFP, the cohomology of HFP, or say it differently, it's pi minus star of maps from HFP to HFP. And it is given an algebra structure, well, FP algebra structure by composition. So the 0-degree part is, as it's easy to see, FP by Whitehead, or many things, and we have seen that endomorphism from HFP to HFP. And there are no things in negative degree, which is the reason for this cohomological indexing convention, because we have seen AI is 0 for all I less than 0, because we have seen that map HFP HFP is the same thing as maps in infinity groups from FP to FP, which is discrete. So there are no positive homotopy groups here. And these are basically all the ones that are easy to compute. But I will give you let me give you another example of a class. So let's consider the abelian group extension. So which is z mod p goes to z mod p squared goes to z mod p goes to 0. So that is indeed a thing. This induces a fiber sequence h z mod p, h z mod p square, h z mod p. Simplest possible way, this is a map of abelian group, so you can deloop this map multiply B infinity, and then the fiber is necessarily H Z mod P because of the long exact sequence. In general, every time you have a short exact sequence of a billion groups, you get a fiber sequence of Eilenberg-MacLane spectra. Using this trick, you deloop the I don't know, the second map, for example, and then the fiber has to be the first. So in particular, we get a boundary map beta from H Z mod P to H Z mod P. That's called the Box-Stein. Yeah, sorry, sigma. This is the Box-Stein homomorphism. And in fact, it turns out that A1 is FP generated by the Box-Stein. This requires some work. Maybe I'll sketch, maybe I'll say a couple of words about how you actually compute the Steenrod algebra. But, okay, oh, and note, that's an important note, beta is 0 on homotopy groups. But it's not null homotopic. Okay, it's 0 in homotopy groups, well, because it can be non-zero either on pi 0 or in pi -1. And in either of these cases, either the source or the target are 0. So not many choices there for what to do on homotopy groups, but it is null homotopic. And how do you show that? You need to find what was it? Yeah, the kernel of beta from, I don't know, do we need, let's do homology. H Z mod P plus 1 X is the image of H Z mod P square right? So it's enough to find some space X and a class here, not in the image of here. And then the image cannot be everything. To show beta as non-zero, it's enough to find a space X and a class HC mod P star X not in the image of HC mod P square X. And that's let me do it the case P equals 2. Since it's simpler, you can take X some real projective space. What do I need? Probably RP2 is enough. Let's say RP infinity, because why not? Since we're at it, it doesn't really matter which one we take, right? And then you can check that the reduction that H Z mod 4 star, 1 RP infinity is 0, but H Z mod 4, H Z mod 2 1 RP infinity is Z mod 2. And well, is it 0? Hold on. It has to be 0. In any case, this map is certainly the 0 map, which is what no, I think it's sorry, it's a Z mod 2 here, but this map is the 0 map. I mean, what is clear, sorry, let me say what is certainly true, is HZ1 RP infinity is 0. That you can check, it's easy. And so let's see. So what is the cellular complex here? We have one cell in each dimension, and the map is multiplication by 2. No, that's 0, that's 0. Yeah, because the kernel of this map is exactly the image of this map. Sorry. Anyway, the point is, okay, such a complex is not hard to construct for every CP. For odd PUs, the equivalent of RP infinity use lens spaces, the odd primary equivalent of RP infinity. But you can just explicitly construct it. And this is some sort, I mean, secretly what I'm using here, let me just be clear, I'm using this is omega sigma h z mod 2. So it is in some sense the universal example. It's the universal guy containing degree 1 cohomology class. And so if the Bochstein is non-zero somewhere, it has to be non-zero here. Since it's the universal example, that's one of those standard tricks. It's trickier to show. In reasoning like this, you can actually show that that the Bochstein is actually a generator of A1. But okay, let me give you a theorem that describes completely the Steenrod algebra. Well, okay, let me think for the first half. So from now on, P equals 2. There are similar formulas for odd prime. They're more complicated and you have to pay attention to signs, which I really don't want to do. Especially since I don't know anyone, even the most experienced person, that does not get confused by the signs here. Really. We should find a better way of dealing with this, but such is life. So let's do P equals 2. So for every I greater or equal than 0, there exists an element square I from HF2 to sigma I HF2 with the following properties. So, okay. Ooh, I forgot. Sorry. So, okay, the first property is square 0 is the identity, and I should call it 1. It's an algebra. Square 1 is the Bochstein. Then we have, so under the equivalence, the isomorphism, sorry, HF2 star. I forgot to mention one important thing. Yeah, sorry. I really should mention, and also, yeah, I'm not sure. Yeah. Okay, the point is if you have alpha in AN, this gives you a map from HF2NX to HF2IX to HF2I plus NX for every X spectrum. That's because, this is homotopy classes of maps from H to sigma F2. This is homotopy classes of maps sigma HF2 by post-composition. Sorry, you probably were wondering what I was saying with the Bochstein. That's exactly the action of the Bochstein that I was describing. Okay, so I have an action of the Steenrod algebra on the cohomology of every spectrum. And I'm going to describe what happens to the product. So under the isomorphism here, which is the QNet formula, you probably saw it only for spaces, but you can deduce quickly from spaces to spectra, or you can even prove it directly from spectra. The way you prove it, you fix a y, and you see that both sides are, so it is a map of cohomology theories that is an isomorphism when X is the sphere, and so it is an isomorphism for every y. By induction on the number of cells. Yeah, so anyway, under the QNet isomorphisms, square n acts on X tensor Y as the sum for I plus j equals n square I X tensor square j y. And that's the Cartan formula. And another way of writing is that if you consider this composite cohomology operation, if you take square bullet, which is just the sum of square I for I greater or equal than 0, you have square bullet of X tensor Y equals square bullet of X tensor square bullet of Y. That's sometimes a more convenient way of rephrasing this. This is for X, Y spectra. And now the Stirnrod squares, oh, sorry, yeah, these guys are called Stirnrod squares, have a particular behavior when you're in the cohomology of a space. So if X is a space, so the cohomology is the same thing as the cohomology of sigma infinity X plus, so we still have the action. We have these two important properties that are called instability properties. So for every little x in Hn x f2, which is hf2 star sigma infinity plus sigma infinity x plus, we have, so square n of x is x squared. That's where the name Stirnrod squares comes from. They're built out of the squaring map. I'm not going to be able to tell you the construction, but the construction is sort of rigged so that this happens. And moreover, you have square I of x is 0 for all I greater than n. And these are called instability of the action. Note that we really need to use that we have a space here to state this property, particularly because you don't have a multiplication on the cohomology of a spectrum, only on the cohomology of a space. Because the multiplication uses the diagonal map that exists for spaces, but there is no map from X to X tensor X for spectra. While for spectra of the form sigma infinity X plus, there is, you just take the diagonal map of the space, and that gives you the multiplication. If you remember, the multiplication was given by the external product followed by pullback along the diagonal map. And so you really need to use the diagonal map. And in particular, moreover, 2 implies that square bullet is a ring map. That's, you post-compose these with pullback along the diagonal, and you get that is a ring map. That's useful. And okay, these are the properties that are easy to remember, the one that I can only remember, and then now I need an additional property, which I need to copy because it's going to be complicated. Questions about the properties so far before I do this? No. Okay, the following property is the Adam relation. So it describes the multiplication in the Steenrod algebra. So for every I less than 2j, we have square I composed with square j as the sum from k that goes from 0 to the floor of 1/2 of this nice binomial coefficient times square I plus j minus k square k. And notice that stuff sort of works because this is in degree I plus j, and this is also in degree I plus j. And these are all the important things in degree I plus j. The only thing you need to work out are the coefficients, and well, that's what they are. And this is actually secretly, you can secretly see this by computation on the cohomology of BCP square, or sorry, in this case, BC4. But that would, it's, yeah, it's what it is. There are other ways of rephrasing it that are maybe more conceptual, but I will need the explicit formulas for today. And that's actually what you end up using in practice most of the time, unfortunately, the explicit formulas. So that's what I'm writing. Note in particular that this guy, so here I said I is less than 2j, but if you look at all the non-zero coefficients here, you have that I plus j minus k is going to be greater or equal than 2k. So in particular, these implies that you can write the every product of terms in which I is less than 2j as a sum of products of terms in which the first term is greater or equal than twice the second in degree. The degree of the first is greater or equal than twice the degree of the second. That is because, so I, if it's non-zero, I has to be greater or equal than 2k, and yeah, j minus k is also greater or equal than 0, I think. Yeah. Anyway, you can, this is a very, it's not very important, the combinatorics, or rather it is important, but the upshot is this corollary. The subalgebra generated by square i's is spanned by monomials of the form square y1 square in with ij greater or equal than twice ij plus 1. And in fact, it turns out that these guys are linearly independent. So let me write these as square I1, and this is called an admissible sequence. Admissibility is this condition here. And then I'm going to take the following theorem, a upper star, the collection square I, as I is an admissible sequence, is a basis for A star over F2. Okay, so these are, I think, all the properties of the steroid algebra that we're going to need. Couple of words about how to actually prove these things. Okay, are there questions about this statement first, though? No. Yes, no, maybe I should.
Okay, so just to make sure I understood. So the subalgebra generated by the SQI, so it's a subalgebra of the Steenrod algebra?
Yeah, it turns out to be everything.
It turns out, okay, and it's spanned as a FPU, as a FP algebra by these monoids.
No, it's spanned as an F2 vector space. I mean, the subalgebra is spanned, right, the subalgebra is spanned by all possible monomials. I'm saying that if you have the Adam relations, you can write every other monomial as a linear combination of these admissible monomials. So
okay, thanks.
And then it turns out that indeed, so this theorem is essentially two statements. The statement that the square i's generate everything, and the statement that all these admissible monomials are linearly independent. So I'm putting them together because you prove them together, but they're sort of two different statements wrapped into one. So the way to prove this is, well, HF2 star HF2. The idea is you can write it as colimit of HF2 star plus n of KF2n. That's because of the standard representation of HF2, because HF2 is the colimit over of, I'm saying colimit, no, of course that's the limit. Sorry. It's the colimit of sigma minus n sigma infinity plus, and sorry, and I should say reduced, KF2n. That's just the standard representation. So to compute the Steenrod algebra, you need to compute the cohomology of these KF2n spaces, which is more complicated than the Steenrod algebra, actually, I thought not much more. And this is computed by an inductive procedure using the Serre spectral sequence. I'm sorry if I'm told that I shouldn't use Serre spectral sequence for the vibration. So we have KF2n, we have a point, and we have the loops, which is KF2n minus 1. And this is non-trivial. There is some very refined analysis you need to do here, but knowing what the answer ought to be helps. Like if you have a guess for what the answer should be for the cohomology of this guy, you can try to do some little comparison of spectral sequences and etc. So Pavel should have told you briefly about the Serre spectral sequence yesterday. I don't want to, I mean, I think he did the case n equals 2 perhaps, or n equals 1, I don't know. I think he said something about how to compute the cohomology of Almer-Maclaurin spaces. And that's essentially that kind of argument, only more complicated. I'll put a reference perhaps in the notes in the book. The book of Mosher and Tangora has a good explanation of this. yeah. Anyway, it's a complicated computation, but you can do every step inductively, and you end up with the formula I told you for the Stirnod algebra, which is what I want to use today. And you have to start with the cohomology of RP infinity, which thankfully we will need also in the following, because RP infinity is also related to Thom spectra. So we start with H RP infinity F2, which perhaps I already said it, I'm not going to remember, but is F2x for degree of x1, which I think was done perhaps in algebraic topology 1, or maybe stated. I'm not sure. A quick way how to see these, actually, you first compute the cohomology of CP infinity using the fiber sequence here. And then you get the cohomology of RP infinity using the fiber sequence which one did I need to use? Yeah, RP infinity, CP infinity, S1. There are two fiber sequences. This comes from the fact that CP infinity is a KZ2, and this is secretly the fiber sequence coming from a fiber sequence of billion groups and looped infinity. And you put all together, you get the cohomology of RP infinity. There are other ways more elementary to compute it, but I like this because it's actually quite straightforward once you learn how to use the Serre spectral sequence. You don't need to put a lot more input than the existence of these two fiber sequences. This one is in particular super easy. It's basically trivial, and this requires a couple more work. But the point is that this fiber sequence, this is the spectral sequence actually degenerates at the E2 page. So there is really nothing to be said for degree reasons. Okay, anyway, we start with this material. If you don't know what the spectral sequence is, don't worry. I'm not using the spectral sequence. I'm just hinting to how these computations are actually done, if you are curious. And these, I think these probably should have been stated. I think this is like one of those things that people always tell you, but no one ever tell you how to prove. I mean, it's easy to see how it is additively, this guy, of course, because you have an explicit cell structure, but you want to understand the multiplicative structure, and that's typically a bit harder. Okay. Okay. Now, I think that's all I want to say about the Stirnod algebra. Oh, no. Well, okay, I'm going to start the computation. I'm going to start to compute how the Stirnod algebra acts on a bunch of spaces, starting with RP infinity. So other questions before doing this? And again, this is going to go to the homotopy type of MO. And the reason I'm starting with RP infinity is that secretly RP infinity is BO1, of course, because O1 is just the group Z-mod 2. And I'm going to build inductively from O1 to On to O, and then use the Thom isomorphism and do some magic, and I will end up knowing everything about MO out of this. By the way, there is a much cleaner way of presenting this computation using the dual Stirnod algebra, but I didn't want to introduce coalgebras and Hopf algebras in this class for lack of time. So I'll present the historically first way of doing this computation by Thom that uses just the Stirnod algebra. Okay. So, okay, question now. Action of square star on the cohomology of Rp infinity. And for brevity now, I'm going to stop writing F2 coefficients every time I have cohomology. All cohomology will be with F2 coefficient. Well, this is actually easy because let's see. Well, square 0 of x is x because because it's the identity. And by the instability, we also have the square 1 of x is x squared because x is in degree 1. And square I of x is 0 for all I greater than 1. And these actually are all the squares. So we know the action on the polynomial generator. In particular, square bullet of x is just x plus x squared. But remember, square bullet was a map of rings. So square bullet of x to the n is square bullet of x to the n, is x plus x squared to the n, which is sum of, for I from 0 to n, of n choose I, x to the n plus I. This is just I plus 2n minus, sorry, am I doing this right? 2n minus I is 2n plus I, sorry. So upshot is square I x is the term in degree x to the n, is the term in degree n plus I of this. So it's the coefficient of x n plus I, which, if I'm not mistaken, should be n choose I minus n. No, this cannot be right. I think I am doing a sign mistake here.
Do you need maybe 2n minus 1?
Oh, no, that's the point. Sorry,
I.
I should do this n plus I. Okay, great. Just a small indexing mistake. Sorry. Right, this is, differently x squared to the I, x to the n minus I, and that's just x n plus I. I was doing the other way around. It was also, of course, a valid thing to do, but the indexing was confusing, and I think this formula is a clean way of stating things. Okay, great. We have completely understand the action of the steering algebra. And if you really, really feel fancy, you can actually verify in this case that the Adam relations are indeed satisfied. It will give you an interesting relation on binomial coefficients for which you can find a combinatorial interpretation of if you feel very clever. Yeah, I'll let it as an exercise if you want to do it. Now we are going to need some information about the cohomology of BOD. So next step is compute the cohomology of BOD with the action of a upper star. And again, I'm just going to give you the fiber sequence for the answer and the fiber sequence that will tell you for from which you can apply the star spectral sequence. And again, when you know what the answer ought to be, it's a lot easier to analyze the star spectral sequence. The idea is that you have a map from O1 to the D into OD, just the inclusion of diagonal matrices. Or if you want, this is the map, this induced sum map BO1 to the D to BOD. And if you want, this is the map that classifies the sum or the product of D copies of the universal line bundle. This gives you a vector bundle of rank D. And this is classified by this map. Eta 1, eta 1 to BO1 to the D. And okay, so we get a map from the cohomology of BOD inside the cohomology of B1D, which by the QNet formula is just, I'm going to call it F2x1xd. And okay, the claim now is that this map is injective with image the symmetric polynomials. Of course, the image is clearly contained in the symmetric polynomials because the action of sigma d here, the map is equivariant for the action of sigma d. So this map is equivariant for the action of sigma d here. And the action of sigma d, by the way, of course, just permutes the generators. This is just a permutation in the QNet formula, permutation of the tensor factors. And so it lands inside the symmetric polynomial. And I'm claiming that this is the case. And the proof, again, is a stereospectral sequence argument, induction on D using the fiber sequence BOD goes to BO, so D plus 1 with fiber SD. And what is this fiber sequence? Well, you have this map. You have clearly this map that induces OD inside OD plus 1 by adding just a 1. Right? We have this map. And I claim that its homotopy fiber is OD modulo OD, OD plus 1 modulo OD, which is identified with SD by taking the last column of your matrix. And why is this the fiber? Well, this is actually a general statement. But in this particular case, you can take the fiber because I give you, remember, an explicit contractible space with a fibration to BOD. And you can actually compute the fiber product there and see that it is exactly SD. Or if you want, another way of seeing that is D, this is the D-dimensional Grassmannian sitting inside the D plus 1 dimensional Grassmannian by sending a vector space V to 1 plus V. And you can see that, well, okay, the homotopy fiber, okay, this is perhaps less obvious that the homotopy fiber is SD, but you can actually explicitly compute it. It is a general statement, though, that if you have an inclusion of a subgroup, this map is just a coset group. I'm sorry. Okay. Is it clear the statement, though? So by using the the fundamental theorem on symmetric polynomial. This is a polynomial ring with degree of vi is I, and vi under this embedding corresponds exactly to for all sigma, well, x j1 x ji, the degree I elementary symmetric polynomial. That's going to be important. These Wi have a name. These are called the Stiefel-Whitney classes. And note then, by taking the colimit in D, you can check that the inclusion of BOD minus 1 into BOD corresponds to quotienting out by WD. You can see that this is the cohomology of this infinite Grassmannian is actually this guy. And it's the action of the Steenrod algebra on this infinite Grassmannian that I want to compute. But, or well, rather, I'm going to tell you the answer because, and explain how we get it, because it's combinatorially a bit painful. But okay, is this statement clear? Oh, by the way, this statement, this claim here has a name. I probably should have said it. It's called the splitting principle. And that's because, as I said, this is the universal map that splits your vector bundle into, as the sum of the line bundles. So what is it saying is that for all that cohomology is concerned, you can always assume that a vector bundle is the sum of the line bundles. So that's a useful statement, and in fact, we're going to use it immediately to compute the action of the Steenrod algebra on it. Why so? Well, because now from this, you can deduce the action of square bullet onto Wi, because square bullet Wi is just the sum of xj1 xji, but these were classes in RP infinity and some BO1, which is RP infinity, and so this is just the sum aj1 plus aj1 squared times aj plus aj squared. And then you can expand and write this in terms of symmetric polynomial, and it is tricky, but not that there are no new ideas that you need to you just expand it. And the upshot is that you get the following formula. Square I of Wj is the sum for t that goes from 0 to I of j plus t minus I minus 1 t e minus t j plus t. And this goes under the name Wu formula, by the way. And a couple of words, but what I mean with the binomial coefficients, because if you look at this formula, you'll notice that the top part of the binomial coefficient might become negative. And here, when I say n choose I literally mean these, which makes sense also for n greater than less than 0. You can just write it. It is an integer, and then you can just reduce it mod 2. Just if I had to like express it in formulas that always have this top part positive, it's going to be even more complicated, and it's just simpler to adopt this. And by the way, since we are working mod 2, we only care about the parity of this integer. So it's not like we are doing very complicated things here. But okay. Whew. And I mean, I'm not going to work out from this formula to the VU formula. You can, hopefully it's clear that with some patience, you can rearrange things so that it gets. And again, this is another one of those situations where it's a lot easier to know the answer, because we can just actually plug in our formulas for the VUI here and expand and see that this coincides with the expansion of this. While if you had to go the other way around, of course, it would require a lot more ingenuity. I have no idea how VU actually came up with the formula in the first place, but you know, it's good for him. Okay, so now we have the cohomology of BO. Questions so far? Because I'm going to claim that now we have also the cohomology of MO, which was what we wanted. Because now recall, by the Thom isomorphism, HF2MO is a module, sorry, it's a free module of rank 1 on HF2 star sigma infinity BO plus. So I actually stated it saying that there is an isomorphism of this, which is an isomorphism of modules. But since we are going to have to be a bit careful with what we're dealing with, I'm going to, so elements of H star MO will be written as P times theta, where P is a polynomial in this, an infinite polynomial in this guise, and theta in HF20 MO is the Thom class. Sometimes people just omit the theta, but I think this gets a lot confusing, because then the action of the string algebra is different. Because in particular, by the Cartan formula, we can get square I of P theta, sorry, square n, but sum I plus j square I P times square j theta. So what this boils down to is that to describe the action of the string algebra on HF2 star MO, we need to understand just the action on theta. I mean, okay, technically I told you only this action on the VWI, but then, you know, using the Cartan formula, again, expanding in all monomials, you can actually write down everything. So the missing step in understanding the steroid algebra, action on H star, HF2 star MO, is understanding it on theta. And now we're going to use an amazing trick to do this.
I'm sorry, before you do the amazing trick, can you explain again why HF2 upper star MO is a free module of rank 1?
That's the Thom isomorphism. So, okay, I'm using that BO is HF2 orientable.
Okay.
Because remember, every vector bundle was always HF2 orientable.
Ah, right. And then MO is the Thom space for the...
It's the Thom spectrum for sigma infinity of BO plus.
Ah, right. Okay. Yes, thanks.
Okay, and remember that MO has has a co-action of this guy. So there is a map from MO to MO tensor sigma infinity plus BO, BO plus, which was just the Thomification of the diagonal map. And this gives you an action of this, it's a co-action of this co-algebra on this thing, but when you apply cohomology, all the codes disappear and you end up with an action of this ring on this module. And I claim that the Thom isomorphism was indeed an isomorphism of modules. And which is just a fancy, I mean, seeing it's a free module of rank 1 is just a fancy way of saying that this is isomorphic to this as module. But it's, I mean, I'm writing this because I want to write the elements as some element of HS of the cohomology of BO times the Thom class. Because then, you know, you have this formula. Okay. So we reduced to compute square J theta. And we're almost there. We're going to use the splitting principle once again. So, okay, recall MO, we add this. We use it also yesterday, on Monday. We add this formula here. This canonical presentation. Well, it's not a canonical presentation, but we have this canonical presentation that comes from the writing BO as the colimit of the BO ends. And we have, so, the reduced cohomology Tn is a free module of rank 1 on the non-reduced cohomology of BON. So I'm going to write H tilde is H BON times theta. And this theta n is actually the restriction of the theta for MO, of course. The pullback of this theta for MO. So we're going to actually see what happens on these things. Oh, because now you get, sorry. O is the limit of the reduced theta m. And we'll see. For n sufficiently big, this will give us our formulas. So let's start with n equals 1. So trick Thom eta 1 is RP infinity again. How is this possible? Well, remember, Tom eta1 was just the cofiber of eta1 minus 0 going into eta1. Or equivalently, the cofiber of the spherical bundle into BO1. But remember, what is this guy? This guy is what I called V1, is the first Stiefel manifold. Because this is exactly, you know, all x in eta1 such that norm of x is 1. But this was exactly, you know, pairs x comma L such that L in R infinity as dimension 1, x is in L, norm of x is 1. And that's what that's what the sphere bundle is, but that's the Stiefel manifold. Because remember, eta1 was just the set of pairs x comma L such that x is in L. And that's contractible because we proved it. So that's BO1, now seen as a pointed space. Careful, because now I'm going to have to take reduced cohomology. And so the reduced cohomology of this guy is the reduced cohomology of RP infinity, which as a module is just this module here. It's just the ideal generated by X. I'm just taking out the zero part, the degree 0 part. But we know the action of the Steenrod algebra over this guy. So X in particular is theta. Unfortunately, this is not quite enough, but we can, because of course this C is only W1. This is only essentially the projection from H upper star MO to H upper star theta eta 1 corresponds to just quotienting out all W2, W3, W, etc. So we want a little bit more. But we can use the splittings principle now. So now you have BO1 to the D mapping to BOD. And here I get my Tom BOD, the guy, Tom eta D, the guy we want to study. And the induced map on Tom spectra is Tom eta 1 smash D. Remember, smash and direct sum. Direct sum of vector bundles gives a mesh of Tom spaces. So we have H tilde, the Tom space of eta D, maps into H tilde of the Tom space of eta 1 tensor D. And under the Tom isomorphism, this is exactly this map here. And the Tom class here goes to the product of the Tom classes here. Sorry, upstairs. Which I guess I called X tensor. So if I call these X1, XD, the ideal generated by the product X1, XD here. And this class is exactly X1, XD. And the point is, this is an injection. So if we want to understand the Tom class, the Steenrod algebra on the Tom class, we can understand it here. So to understand square I theta, oh sorry, square bullet theta, it's enough to understand square bullet of x1 xd. Is it clear, this step? Because now this is square bullet x1, blah, 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 square bullet xd. But okay. That's x1 plus x1 square, xd plus xd square. And if you, okay, I guess. Now let me actually do this. I'm skipping so many steps. Let me actually do this computation since it's doable. This is the sum. So you have one monomial for each subset. So okay, now let's collect x1 xd, which was our theta. So plus xd. That we can certainly do. And so we get theta times the sum over all subsets xds. But that's, if you look at what it means, this is theta times w0, which, sorry, is 1, w1, w2, wd. Because that's literally the sum of all the elementary symmetric polynomials. So what it boils down is square I theta is wi theta for I lesser or equal than d. And when you let d go to infinity, this formula just holds, no restriction on I. Whew. We're done. We have completely understood the action on the steroid algebra. By the way, this sometimes is used as the definition of the WIs in for example, in the book by Milner and Stashev on characteristic classes. So I'm also showing you that the definition I gave you of the WIs earlier actually coincides with the definition of WIs in the literature. Of course, there are other proofs of this, but since we had to do it anyway. So, okay. Now there is a super complicated combinatorial thing, but I'll try to motivate it 1 second. But first, are there questions about this formula? So actually, let me circle the important part, since we're going to let d go to infinity anyway. No, we are not going to meddle with finite Grassmannians anymore. We have our complete description of H star MO. Okay. So now, homotopy type of MO. Okay, so the first remark 1. So remember we have H star MO is F2 W1 etc. times theta. This is called theta if you want it. Canonically is a free module of rank 1 over this ring with class theta. And we have this action on square 1y, and we had the Wu formula earlier here for the action on Wj. And now we understand everything. So the first remark is pi star MO is 2 torsion. And there are purely homotopical ways of doing this, but for example, computing the cohomology of the Grassmannian with FP coefficients for every P, and then rationally, and etc., and see that there is nothing interesting going on. But since we proved the Pontryagin-Thom theorem, it's enough to show that N, the unoriented Bordiism group, is 2 torsion. Because if we have a class here, we need to show that the class of M disjoint N is trivial. But M disjoint union M, so 2M is the class of M disjoint union M, and that's the class of the boundary of the cylinder. So that's 0. And here I am using that I'm unoriented, because normally the orientations of the 2 ends of the boundary would be different. But since we are completely ignoring orientation data in this case, there is no. In fact, it's an F2 vector space, and in fact, we will explicitly write down a basis for this F2 vector space. Well, okay, I'm not going to, you can actually give explicit manifolds that give a basis, but I'm just going to construct the homotopy classes and let you do the tricks. So, okay, now there is the claim. Let me define. So let omega is A1, A2, blah, 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 AR be a partition of M. That is, it's an unordered family of non-integers, i.e. non-ordered family of integers such that sum of AI is M. Okay? Then I want to define a class X omega in the cohomology of MO. And I'll define it again by giving you a class in the cohomology of Thom eta D for any D that will clearly restrict to each other. This X omega is a sum of T1 A1, T sigma 1 A1. Well, okay. Let me write it like this: is the symmetrization of this polynomial. So I give you a monomial, but I need to sum it all its conjugates, so that I get a symmetric. Oh, sorry, I call them X here. Why I'm using T here? Not sure. So you have this guy, and it can be written as some polynomials in the WIs. In general, it's, well, we have an algorithm for doing that, if you remember the formulas on the fundamental theorem of symmetric functions, but might be unexplicit, so I'm going to just write it in terms of this. This sits inside. Well, this is. No, sorry. Of course. I'm so sorry. These classes are not in the cohomology of Thom space, they're cohomology of the Grassmannian. Of course. I mean, what I wrote were not classes. And the problem is that Thom's original paper, which I am following here, does not distinguish between the cohomology of the Thom space and the cohomology of the Grassmannian, since they are canonically identified, just with a different Steenrod algebra action. So I forgot to, I made a mistake here in copying things. But I prefer to keep them separate, since they are separate groups if canonically identified. Okay, you have these classes, and this X omega form a basis, an additive basis of H star BO. These are basically a parametrization of all, symmetrization of all possible monomials. So, you know, additive basis. Therefore, X omega theta for an additive basis for H star MO. Okay. Now, okay, there is a super complicated combinatorial argument here that I think I'm just going to sketch. But the point, let me say that omega is non-dyadic if none of the AI is of the form 2 to the m minus 1. Okay, I have a partition in elements that are not not a power of 2 minus 1. And here comes the theorem, which is the key computation that makes this work. So H upper star of MO is a free A upper star module on H omega theta, where omega runs through, actually, parentheses here, all non-dyadic partitions. And this is actually not super trivial to prove, although I gave you all the, I mean, you can see that I told you everything explicitly, right? You have explicit formulas for everything, but the combinatorics here is trickier. So the way to prove it is actually to filter this guy as an A upper star module. Well, to filter this guy, yeah, the A upper star module, and prove the statement on the associated gradient. And the filtration is given by total degree of the partition and number of dyadic variables. So the idea is filter H star MO by the subspaces Fs MO spanned by H omega has, I can never remember if I have to do an increasing or decreasing filtration here. I think decreasing, less or equal than S dyadic elements. And then you can actually, compute everything and see that the associated graded is free, and so the original guy was free. This is a filtration by A upper star submodules, if I've chosen the direction correctly, hopefully. This needs to be verified. This is not obvious, but I gave you formulas so you can actually check. And the associated graded is free. No, sorry, it's not a filtration by upper star. No, yeah, that's a filtration by upper star submodules. Yeah, that's true. And I mean, that's yeah, I think that's the right order in which to do things. And I mean, again, I don't want to. I mean, if I had more time, I would do a complete the complete proof here. But hopefully, you can see how you can just write down. The point is that in the associated graded, a lot of this stem reduction just dies, so it's a lot easier to see that. It's a lot easier to see that things are linearly independent and etc. Okay, questions about the statement and or the sketch? No. Okay, because now from these we conclude. So now, okay. Now we go actually the actual theorem, right, Tom? The map from MO to the sum, the degree HF2, where omega runs on non-dyadic, is a homotopy equivalence. And this is just sum of these maps. And this actually tells us also what its homotopy groups are, of course. And in fact, a more refined, well, okay, I'll say later what a more refined analysis can tell us. The proof is easy. By the previous result, this is an equivalence on HF2 cohomology. Because, because on HF2 cohomology is exactly this map here, which we claimed to be an isomorphism, right? Moreover, it is an iso on HZ2 inverted cohomology. That's because both sides are 0. . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . 0 . Hence, it is an iso on HZ cohomology by putting together with the fracture square. Well, okay. It's easier than the fracture square, but since we have the fracture square, we might as well use it. But then it is an equivalence, since both sides are connective. That's by Whitehead theorem. It was also in an exercise. If you have a spectrum if you have a connective spectrum with HZ homology trivial, then it has to be the zero spectrum. All homotopy groups are zero. And you need connective here, of course, because you have to start the induction somewhere. And then last week exercise, there was actually an example of a non-connective spectrum with trivial integral homology. That was Ku mod B. But in this case, both sides are manifestly connective. Since remember, this is just a colimit of spheres. So this is connective and this is, well, this is connective. I mean, look at it. Its homotopy groups are definitely all in positive degree. And that's the end of the proof. And therefore, we have a description of all its Borgism group of unoriented manifolds. And as far as I know, it is the only way of proving it, actually. I don't know of any other proof. I mean, this is part of this theorem is part of the motivations why people were inspired at defining spectra. Because all these, if you read Tom's original paper, it actually works with just formal limits of cohomologies and homotopy and etc. of Tom spaces. And people started thinking, oh, there must be a better way of encoding this data, and so they come up with the notion of spectrum, and that was not the only. There is also the Brown representability theorem, of course, was an important motivation. But yeah, so yeah, I think that's all I want to say for today. And oh, and notice that the corollary, of course, the map MO to HF2 has a section. Okay, that's obvious. But since we used it last time, let me point it out. So you can see these are natural geometric questions. I mean, what are the Borgism groups? When is that? In fact, you can look at it more carefully and see that it tells you that a manifold is a boundary if and only if all the Stiefel-Whitney classes of its tangent bundle are trivial. By Stiefel-Whitney classes of a bundle, I mean the pullback of the. If you look carefully at what we've done today, so there are these natural, geometric questions. When is a manifold a boundary? What's the solution to the Stirnrod problem? And you can turn these into homotopy theoretical questions. And actually, let me remark a more careful analysis gives MO, well, homotopy, in fact, much more than homotopy, but ring structure given by the tensor product of vector bundles at the level of spaces. You have a map, coming from BOD times BOD prime, BOD prime, tensor product of vector spaces, which encodes the Cartesian products of manifolds. And if you look at this, in fact, all the computation I did is enough to deduce. And from these, you can actually write these as what was the name of these generators? Yeah, di. I different to m minus 1 for degree of di is I. If you look at it additively, is exactly the group I described before. But this is the way usually the formula is written, leveraging the multiplicative structure to get a shorter description. I'm out of time, so I don't think I am going to say anything more about the multiplicative structure, but really all the ingredients are there. Are there questions? If there are no questions, I'll also say that pi star mu can be computed. These are the Bordism groups of manifolds with a complex structure on the stable normal bundle. They're called almost complex manifolds. Sorry, no, they're not almost complex. They're even less than almost complex manifold, but okay. If you know what I mean. The normal bundle can be given a complex structure. And this is a very important ring. As I said, it turns out to run the show in the homotopy groups. And pi star of MSO, the oriented Bordism group, is also interesting and can also be, well, computed. I put it between quotes because I'm not aware of a nice closed formula, unfortunately. The integral part, when you invert the two, it's kind of nice, but the two torsion part gets a bit unpleasant. But in some level, you have everything in your hand. You know, the step is always the same. You compute the mod 2 cohomology and then study the steen reduction there, and actually do a more refined analysis than I say words next time when I talk about the Adams spectral sequence to get the homotopy. Here we lucked out because the steen reduction was free. And so it was a simple argument, but you can do a more refined study, which we will do next time.
Okay, so I have a question. Namely, is there an easy way to relate from this point of view Stiefel-Whitney classes and Chern classes, say of vector bundles and complex manifolds?
I mean, yes and no, in the sense that, yeah, I mean, so we have sort of seen that the F2 cohomology of BO is this infinite ring, right? And the equivalent version for Chern classes is that the integral cohomology of this guy is this integral ring. So here the degree of Wi is I, here the degree of the Chern guy is 2I. These are called Chern classes. And this is, the proof is pretty much the same as the one I said for Wi. Use the fact, though, that every complex vector bundle is HZ orientable, not just HF2 orientable, to get a stronger statement. And of course, you have maps from BO to BU that are complexification and from BU to BO. And you can, in fact, tell us exactly what they do on cohomology. Now, if you ask me exactly what they do under this description, you could catch me unprepared.
No, it's perfect. Yeah, so the BU thing is what I wanted to see. Okay, cool.
Yeah, that's in fact the first step in understanding the homotopy groups of MO, the same way in which the cohomology of the Grossmanian was the first step in understanding the homotopy groups of MO. but that's not hard. And by the way, these can also be computed. BO and BU actually have explicit cell structures that you can write down if you are a representation theorist. And you can actually see the cells. Or since Joachim is here, Joachim is here, or if you know the Jelinek-Birol decomposition, actually, that's another way of getting these explicit cell structures. So I could have just given you a cell structure for the Grassmannian by hand, just writing it down the cells and say, oh, so the cohomology is this, but it feels a bit cheaty. I think that was historically the first proof. Not sure, but anyway. Okay, further questions? No? Then I think I'll call it off for today. And I hope this was interesting and it's a bit sketchy. But yeah, see you on Monday. I think next week is the last week, right? If I'm not mistaken by the academic calendar. So I'll say some few words about the Adams spectral sequence. All right.
Okay, thanks a lot. See you on Monday.
You.